So, now that we've proved Euler's formula, I'll be able to show you my main argument here. Let us just ponder this for a moment. We have e to the I theta equals cosine theta plus I of the sine of theta. Now this is very interesting, very interesting to prove, as we've seen. But let's just say, let's just enter some values for theta, for our input. And then from that we can measure these two output values, which is really, we can think of it as one output value being a complex number. But of course it has two different parts. So let's say theta, in one column, I suppose. And we'll say cosine theta plus I sine theta. Let's just start with 0. And I think for our purposes, just for now, we'll probably continue with an interval of pi over 2. You may know, as it is, that for various reasons I have been persuaded that pi over 2 may be a better circle constant to use rather than pi. Some people prefer tau equal to 2 pi. Well, pi over 2, that's another candidate, and you may see why in a moment. So let's fill in. For our first value, you'll probably recall that the cosine of 0 is pretty clearly just 1. And we substitute 0 for theta in that latter term right there, so sine of 0, and that term just crosses off for that. So, and this is pretty clear from what we know in the past, because we know if we were to substitute 0 in for that exponent, well, e to the 0 would simply equal to 1, and that's very good. So now moving on, e to the I times the quantity of pi over 2. If we just focused on this part of the equation, e to the I times the quantity pi over 2, well, that would appear unsolvable, probably. But then, of course, with our proof, we just substitute the value of theta. So cosine pi over 2, well, we know that is 0, actually, right, if we check the unit circle. So this is basically it. The cosine value of pi over 2, that's the x-coordinate, so 0. And then we have plus I sine of pi over 2. Sine of pi over 2 is, we can see from the same diagram, it's equal to 1. So basically we get 0 plus 1 times I, or just I. And so similarly for pi, we can substitute that in for theta. Cosine at pi is negative 1, we see that. And the sine is 0. There's, the y-coordinate is simply 0. So at that point we can just say this is negative 1. At 3 pi over 2, well, cosine 3 pi over 2, that's the x-coordinate 0, and then the y-coordinate is negative 1. So I'm going to say 0 minus I, really, so negative I. And then 2 pi, which is 1 full revolution. We can really think of that as being the same point on the unit circle as 0, so it would really return the same values, in our case. And so, of course, that would simply be, you've probably guessed it's just 1, and that is certainly true. Now we could continue this, of course, for really as long as we want. I had 5 pi over 2 right here, so that would be 2 revolutions. Well, I'm sorry, 1 full revolution, because that's 2 pi radians, and then plus a half pi, and that's just following the same pattern. So it would be cosine is equal to 0, and then the sine of that is 1. So it's really I. Well, this is a pattern, really. This first of all, let me explain that what this demonstrates is that e to the I theta is a cyclic function, and that is very extremely important to note about, well, e to the x, and basically, as I will demonstrate, for all exponential functions, that they have cyclic properties, just like cosine and sine. Now, in the public school system, they do teach you that sine and cosine are cyclic. We see graphs of them, we see how they repeat through the values, and that's all well and good, but it's even more fascinating when we think of exponential functions using the complex numbers or imaginary numbers. And just for perfect clarity, this is actually one of the reasons that I prefer pi over 2 as that circle constant, because with this table or paradigm, whatever you want to call it, through this process of getting these values for e to the I theta, we are really, through this process, actually getting the powers of I. And you may have noted this already, that these are the powers of I. You know, we start with I to the first. I'll start a new column for us. So this really shows you, this is just meant to show you what happens when we substitute different values for theta into this formula. And the most common, just so you know, the most common thing that they'll teach you in math class, most likely, of course, this is sort of an inference by me. I don't actually know. I haven't actually taken calculus yet. But from what I've heard, they especially stress the identity, which is e to the I pi. E to the I pi. You may have seen this before, this very interesting property, and it is very interesting and quite beautiful, and that is certainly true, but and if I say e to the I pi, I'll write the whole identity. Plus 1 equals 0. This is what we see all the time. This is probably what they emphasize in the public school system. E to the I pi plus 1 equals 0. And that's very true. We can see from this table. If we substitute pi in for theta, we get negative 1. So just, you know, simple algebraic manipulation, and we get e to the I pi plus 1 would then equal 0. And that's very good. That's certainly good. But as I said, my objective, one of my objectives through this series, is actually to show you a broader scope of the truth of mathematics, and you know why things are true, and how these things can be extended or expanded, basically. And so now that you've seen this pattern, I think you're ready to see my main argument on why the natural log of 1 may not really equal 0. So that's what I'll show you next. So we have e to the I theta equals cosine theta plus I sine theta. Very interesting. I cannot stress it enough. Amazing identity right there. I hope that you are enthused by it, because it's, I mean, this very short formula that takes a long time to prove, but is just so pleasing every time you write it. Anyway, on to my argument. If we have the natural log of 1, or as mathematicians, they usually just say just log by itself for log base e, actually. At least that's what I've seen in my experience. They simply put log, and that's very interesting how e has become kind of, you know, recognized as a natural, elegant kind of number, enough to make it our standard for log. When mathematicians write it, of course. It's probably different for engineers or, you know, calculus students. But anyway, as I was saying, if we have ln of 1 equals gamma, I just chose gamma because it's cool, then we know, we're basically saying that e to the gamma equals 1. And that's just a property of logarithms. We want imaginary values of our gamma, so we actually want imaginary solutions, basically, to this equation. So gamma equals, let's say it equals I theta, actually. Okay, so e to the I theta now equals 1. And so now through substitution, cosine theta plus I sine theta, I'm running low on battery power, actually. Or not battery, I'm running low on memory, actually, on my SD card, so perhaps I should hurry this up. And so if we want cosine theta plus I sine theta to equal 1, what I conclude is that at this point we want cosine theta basically to equal 1 and sine theta to equal 0. At least that is one way of solving this equation. And so this system describes really a point on the unit circle. It's where cosine is equal to 1 and sine is equal to 0. And you can probably get where I'm going here. I'm saying that the x-coordinate must be 1 and y-coordinate must be 0. So the solutions of this, in terms of theta, must be really the values for theta which solve this system. Well, there's an infinite set of those values, right? That forms an infinite set. Not just 0, but if you think about it, it's 0, and it's also positive 2 pi, and it's positive 4 pi, and 6 pi, and 8 pi, because it's basically every revolution, every full revolution. And a revolution is 2k pi, really. So let's say it's 2k pi for every value of k in z, the set of integers. And so this is what I conclude. My verdict is that the ln of 1 is not just 0, but it is all integer multiples of 2i pi. And I say 2i pi, bear in mind, because this is just the value of theta. Right, and if we want the exponent, if we want to find gamma, gamma we've defined to be equal to I theta, so it's I times this. So let me know what you think. You can let me know if you have any input. As usual, thank you for watching. Please feel free to leave any comments or questions. And I'll see you next time.